Okay, for Module 8C, the last part of Chapter 8, we're going to still talk about the chi-square goodness of fit test, but we're going to talk about one aspect of it that I've mentioned before, but we haven't seen any examples, and that's this concept of estimating parameters to get the null expectations and how that affects the test. Apologies for yet another kind of boring Hardy-Weinberg example. These are just the ones that spring to mind for me. So previous work indicates that a frequency of the big R allele is 75% in a diploid plant. Sorry, this is supposed to be 75%, not 0.075%. A researcher wants to see if this fact and the Hardy-Weinberg model predict genotypic frequencies. So the null hypothesis here is the genotypic frequencies would be what's expected by Hardy-Weinberg, which is just the binomial expectation. 0.75 squared for the big R homozygotes, 2 times 0.75 times 0.25, 2 being the binomial coefficient for the heterozygotes, and the probability of the little r being 0.25 squared. Okay, and then the alternative is just that the genotypic frequencies will differ from these expectations. Remember, these are the population frequencies in the sense that if we had infinite sampling from this genetic population. So the researcher, they genotyped 200 individuals, and these are the data down here. And so it sounds like a chi-square because we've got a categorical data type, this genotype, and indeed we can do a chi-square. So we set up a table for our 3 categories, and there's the data that I just showed. The expectations come from this Hardy-Weinberg, so just what I had previously indicated in the population size. 1 minus p squared is 200 times 0.25 squared for the little a homozygotes. So that's 21.5. And similarly, 75 for the heterozygotes and 112.5 for the big A. So if we just sort of eyeball the data, we notice that we see too few big A homozygotes, way more little a homozygotes, and also quite a bit more heterozygotes than we would have expected. We can see if that's a significant difference by calculating the chi-square test statistic, right? Remember that the numerators are the deviations squared. Before we square them, we can see that they should all add up to 0, and we see this big deficit here, this negative number. We saw a lot fewer of the big A homozygotes than we expected. So when we plug through the arithmetic there, we get these chi-squared terms, and they're all pretty substantial, quite a bit bigger than 1. And the total chi-square test statistic is 13.69. That's by summing all of these, of course. Okay, so now we want to compare this to the null distribution for the chi-square test. We need to know the degrees of freedom. And remember, the degrees of freedom is the number of categories, k, minus the number of parameters we estimated from our testing data in order to calculate the expectations, minus 1. So we didn't estimate anything. We were told 75% was the allele frequency, and that's what we used in Hardy-Weinberg. We were told the equations, they basically come from the binomial, this Hardy-Weinberg assumption. So 3 minus 0 parameters estimated minus 1 more parameter gives us 2 degrees of freedom. We can look in the table. Once again, degrees of freedom, we look in the second row, and we look at the right tail probabilities. For the 0.05 level, the critical value is 5.99. For the 2.5% level, it's 7.38. For the 1% level, it's 9.21. We just kind of keep going out. Our test statistic was 13.69, so we keep going rightward in the table. We're still larger than that critical value. 13.82 is the next one. We're not quite as large as that, right? So the critical value for the 0.005 level is 10.6. The critical value for the 0.001 level is 13.82, and our test statistic falls in between that. That means our p-value is going to fall in between these numbers. And it's usually more important to convey to people how small the p-value is when we have a tiny p-value. So we don't even have to necessarily mention that it's greater than 0.001. The key thing is the p-value is less than 0.005. Okay, so we've bracketed the test statistic with 2 critical values. That means the p-value is bracketed by these alpha levels that were associated with those critical values. Okay, so that's a tiny p-value. So using our standard alpha level of 0.05, we would reject the null hypothesis, and we might conclude something like, in the study of 200 genotypic plants, genotypic proportions deviated significantly from the expectations of the Hardy-Weinberg equilibrium with an allele frequency of 0.75. And so that's where we put since we said significantly, we put our test statistic and our degrees of freedom and our p-value that back up that statement. And then we'd see, when we want to describe the data, somehow we use summary statistics. We'd say something like fewer big A genotypes than expected. We'd probably have a figure for this, as we mentioned, chi-square expectations versus observations are frequently shown as grouped bar charts rather than just a bunch of statistics, but you could do it either way. Okay, so hopefully that seems familiar and makes sense. But then imagine a colleague tells the researcher, that 75% allele frequency you use there, that's just a rough guess from another population. It's not like a true value that we know from studying this population in great detail. So if you're interested in whether there's evidence of something causing a deviation from Hardy-Weinberg, you should just test for Hardy-Weinberg equilibrium here, not Hardy-Weinberg with this specific allele frequency, right? And so we see the previous null hypothesis. It was fine. It sort of works, and we got a valid conclusion. But it's a sort of a weird null hypothesis. I'm going to go back several slides and look at it again. It's the genotypic frequencies are going to be all of these numbers that's coming from a combination of 75% allele frequency and Hardy-Weinberg assumptions. So there's sort of two assumptions going into that null. So when we reject the null, we don't know what part of it is wrong. So often we'll want to do something that's a little bit more targeted in terms of the null. We'd say something like, let's just have a null hypothesis that says the genotypic proportions are going to follow the Hardy-Weinberg. P squared for the big R, 2p times 1 minus p for the heterozygote, and 1 minus p squared for the other homozygote. But we don't know what the true population proportion of the big R allele is. But it's still a reasonably specific point in parameter space, but there's this complication that we don't know what this value is. The alternative here is just that the genotypic frequencies do not follow those proportions for any value of p. So that's a more general null hypothesis in the sense that if we reject this, we're saying something about Hardy-Weinberg for any value of p, but we can still test the Hardy-Weinberg proportions. Okay, so here's the data again, and here's our expectations according to the Hardy-Weinberg equilibrium, or the binomial if you prefer to call it that, since we know it and love it from chapter 7. It's just the binomial distribution. Well, of course we need numbers for the expectations, not just formulas for the expectations. So we need to fill in something there. So what do we do? Well, they've actually sampled 400 gene copies because they have 200 individuals, and it said it was diploid, so there's 2 plants, 2 gene copies per plant. So you can actually estimate the frequency of big A allele to come up with this. We won't get P, that's the population proportion of that big A allele, but we can get P hat, an estimate of that. So we can use that to come up with our expectations. So how do we do that? Well, it's 2 times the number of individuals. Every homozygote big A carries 2 copies of the gene, so we would add 2 there, and every heterozygote has just 1 copy of the gene, so we have a coefficient of 1 there. So in other words, it's just counting up the observed fraction in category 3 plus the observed in category 2, right? So these numbers up here. So 2 times 89 plus 90, all divided by 2 times 200, and we get a frequency of 0.67. So 67% of the alleles that show up in our sample of 400 gene copies are the big A type, right? So now we've got an estimate of P. We have P hat. So P hat equals 0.67. 1 minus P hat equals 0.33. That's the estimate of the little. I'm afraid that I used big R, little r, and now I've switched to big A, little a. Sorry about that, but I meant the same system. I just messed up on what I was calling the genotypes here. But anyways, we've got allele frequencies, and we're ready to put our expectations in terms of numbers. So just plugging through the math here, 200 times, that's the sample size, the number of individuals we've genotyped. 0.33 squared is the expected frequency of this type of homozygote. And there's our 21.78. Okay, so you can plug through that math and check it. I don't think I made any errors there. Just focusing on the expected column, just taking away the equation, we can see that these numbers are actually quite close, observed minus expected. And if we start to calculate the chi-squared terms, we see very small numerators. Once again, they add up the numerators before you square them. I forgot the squareds here. These all should be squared before we calculate. Sorry about that. Before we do the squaring, it would add up to 0 because you can't have a net deficit or excess. But they're all tiny numbers, and when we do the squaring and divide them by their expectations, we get these chi-square terms over here, and a total chi-square term, a very, very small chi-square test statistic of 0.087. So we're almost certainly not going to reject. We haven't looked up the critical values yet, but I've done a lot of chi-square tests in my life, and that's a tiny chi-square value. But before we look it up, we need to know what the degrees of freedom are. The degrees of freedom, remember, are k, number of categories, minus the number of parameters estimated to come up with the expectations for our null hypothesis, minus 1. And so this is the first time we've seen sorry, I messed that up again too. This is the first time we've seen a non-zero number here. The number of parameters estimated, we estimated p hat. That's one parameter. So 3 minus 1 gives us a total of 1. Okay. So we lose a degree of freedom by estimating p hat with our testing data in order to calculate these expectations. In order to get these expectations, we had to use our observed data. And so that means that we're sort of matching the expectations to the data on one level. And so it's a little bit unsurprising that we get better match between the expected and observed because we've used the data to calculate a portion of the expectations. Okay, so we've lost a degree of freedom there, and that means that the appropriate chi-square to look at is the chi-square with 1 degree of freedom. You have to think about this degrees of freedom in terms of how many ways the data can surprise you. If I told you that the sample size was 200 and that p hat was estimated from our data of 0.67, that's sort of before we pulled out the expectations, we had to do that much work or get that much information. Then there's really only one way, one direction or dimension or one way, however you want to think about this, that the data can surprise you, and that's why the degrees of freedom is 1. What do I mean by that? If we have this background knowledge again and we don't know what let's just say the heterozygotes are, the number of heterozygotes are, the data can surprise you there, right? You could have more or fewer than you expected. So that's a way in which the data can surprise you. But if you learned that the number of heterozygotes was 90, then you can actually solve for the number of big A homozygotes or little a homozygotes. So this was the formula here for p hat. That is equal to 0.67. If I put in 90 here, I can solve for the number of big A. So here I'm going through, I multiply both sides by 400 to get this form. I subtract 90 from both sides to get that. I divide by 2. And so this tells me if we've got these facts and one more bit of information, we can figure out that there must be 89 big A homozygotes in that data set. And of course, the little a is just the total sample size minus the other possibilities. So 200 minus the 89 that we just figured out and minus the 90 that we were told. So it's 21, right? So the idea here is, we learn something about the data can surprise us in this direction, but really once it does that, everything else has to be, we have to be able to figure that out. So there's no sort of degrees of freedom of the data to vary from expectations. So that's where the term degrees of freedom comes from. So that's why the degrees of freedom is 1. Once again, this is incorrect on the slide. Sorry about that. Degrees of freedom 1. If we look up the chi-square table with 1 degree of freedom, we get 3.84. Our chi-square test statistic is much smaller than that, so we do not reject at the 0.05 level. So the population looks very close to Hardy-Weinberg proportions if the p is actually 0.67. We don't know that's the true population frequency of the dominant allele, but we certainly can't reject Hardy-Weinberg if we just go in and say, does this population look like it might be in Hardy-Weinberg, which is appropriate in this case because I actually simulated these data in R according to the Hardy-Weinberg equilibrium. So the point is that by fitting the data, notice the chi-square, this is the same data, the chi-square term is tiny here, and way before, if I go back several slides, the chi-square was enormous if we came in with a specific idea of what the allele frequency was. So fitting the data, using it to come up with our expectations, made the data look the expectations look a lot more like the observed data. So the chi-square tends to shrink, and so we lose a degree of freedom, and we have to look at a different chi-square distribution as our null distribution. So hope that makes sense. We're going to see some more examples of this in the next chapter where we fit expectations from the data and we lose degrees of freedom. But just wanted to walk through one example in a general case before we see that in the chapter on contingency tables. Okay.